Hello everyone, welcome everyone back our lesson, Introduction to the Quantum Computing and Programming. So today we will learn about the linear operators. This one is very important to represent the quantum state and transform. Yeah, I wouldn't say the transform because this kind of linear operators so can help to combine two vector, or we can support a kind of transformation. Yeah, transformation. Okay, so if you see in this figure, you can see we have 7 speed. We have quantum gate, we have a unitary operator, we have a linear operator, and linear mapping. So over here, we already learned about this part, right? And we learn now we learn about this part, because this part we need to combine and try, help you to transform between this one and this one, linear mapping. Yeah, so it's very important, yeah, to show unitary the operator we have mentioned in this part 2. Yeah, so because this one is specified for fundamental the properties for quantum gate. Yeah, quantum gate, and so we can satisfy some the property for quantum operator. So this part for the mathematics include a lot of mathematics, very important. Yeah, I hope everyone can got the point. Yeah. Okay, we will look a kind of more simple example. Okay, for example, we have one vector v. Yeah, in the vector space, complex vector. Yeah, complex vector. Remember we have c. Okay, c in a complex vector, and this is dimension dim. Vector v is equal to n. So you see here we have a 1, 2, n. This n. Okay, so we have a dim v the vector. So and we have a vector. This one is quantum. So we have a b is kind of basis. So if you see over here is kind of different. Okay, basis we have this one is square, and this one we have yes. This one is parenthesis. Yeah, parenthesis. Yeah, so this one is kind of different. Yeah, remember with symbol is different. Okay, to make sure you're not confused between the basis or the vector. Okay, now we have a basis vector. We have a vector space. How we can operate the linear. How we define the linear operator. So over here we define the linear operator T. It's linear. Remember, from the V to V. So it means we transform the vector when we need to satisfy for the property. If have two value in this kind of vector V space, yeah, this is a vector V space. If these two the vector, and two vector in this kind of complex vector, and if we multiply the value in complex vector and in the vector space, so we can split the complex vector outside. Yeah, you cannot move to the outside. You will see from this one to the C can move out. Yes, move out. Sorry, move out like this, and D can move out. Yeah, but C and D needs to in complex vector. Okay, if C and D in the vector V, this formula is incorrect. Okay, yeah. So make sure you notice about this requirement. Yes, this requirement. And when we have the similar, when we have vector V in vector space, yeah. And we have a kind of a series. This axis. Okay, this axis one of the number in complex vector. So when we multiply the one vector with a kind of the constant in the complex vector, so it's equal. You can multiply one by one. Yeah, you can see. Yeah, you multiply one by one. Yeah, one by one, and after you can have this kind of basis. Yeah, this kind of basis. So the vector V, or the vector representation for vector V, after we with the basis vector b, so we can equal to this one is n, okay, and what is y1? That is we have one column and the rows, and this kind of value you can see over here. Get from this linear, this kind of linear operator, okay, linear. So you can see this one, yeah, okay, use this kind of value. So if you see about the linear, this kind of linear formula, so you can transform to the kind of matrix, yeah, you kind of matrix. Matrix includes the the n rows or the one column, yeah. So it's similar in the property of linear operator. We can easily, yeah, after with this one, if we have a linear, this kind of linear, right? We have a linear combination. If we have a linear operator, so we can move this kind of constant value from the outside, yeah. This from here, yeah. You can move from outside. So that means the constant value or the number in the complex vector doesn't matter is in or out. So we can make a map, a map between the linear operator and the linear the combination. So we can map follow this formula, and the mapping properties for the linear this linear operator, okay, linear operator can follow this one, yeah, can follow. Remember we have we have this part, yeah, we have basis, okay, so we have basis, and after we choose a mapper, so this one basis after we use a linear operator, so we can follow this kind of value. For example, after we linear operator from the T, this linear from V vector space in vector space, okay. So, but over here have some special value. You have a no, this have no entry or no other values in the after you linear is still equal to 0, okay. For example, you can this one, you have this one in linear combination, right? This linear combination. After you equal to linear combination, you can move this on 0 to out. Yeah. So 0, if 0 multiplied with any value is equal to 0, right? With any equal to 0, right? So 0 multiplied with linear combiner for 0. Sim, so it's equal to this part equal to 0. Yeah, that's very important. It's called cancel law, the cancel law. Yeah, we linear or the cancel law in the linear operator is equal to the 0 the value. Okay, now we look more abstract. After we transform between the 1 by 1, so for example, we have the function f. We transform from the A and B. We transform, okay? If you see this kind of transform, or the one of the function, the value via the function f, yeah, function f. So if for all the alpha the value in A and maybe axis no axis B. So with this kind of transform. And the f function can make, yeah, this a, right? This alpha or a in this one, right? This one for O, and b, this one is b equal to this one, right? So that is the one that remind you after you transform, yeah. So the function, yeah, the function. The value, the calculation equal to the number in the new space, yeah, so B is called the 1, 1. So it's a 1, 1. This value only on the value, yeah, you see, I have 1. If this one is A and B is a different, so the function will be have a different. If the same, so they wouldn't be the same, yeah. So about the onto, so this one is, I think, is for all the value in B, and we exist on the this is on exist A in the A in this A, yeah, alpha or A, yeah, A capital. So we can see if we exist this kind of transformation, so we'll say this kind of, the onto, yeah, the onto the function. And the kernel and the range, so okay, the kernel that means the kernel of operator equal to 0 is kind of the children set for the vector V. Is similar, the range of this one, and this kind of formula, and try to prove for the kernel and range subspace for vector V. So over here, the key point is we have, if we have a linear operator is a kind of sub for the vector V. So after we change a kernel, is we have a same, the formula, and this is how proof. Yeah, so you can look more about details. So this kind of step to prove that kind of formula, and after we have a one-to-one, and we have a kernel, and we have the onto the function. So how we can combine and try to make a kind of condition transformation. So we'll look more about next part. So this part we only focus on about the formula is called the kernel, and we have 1-1. We have onto, and we have the final. This one we have about the linear operator. Yeah, linear operator. Linear operator T. Yeah. Okay, that is part for our today's lesson. Yeah. See you in the next part. We will clarify the other how we can calculate a linear operator. Yeah.